Okay, so today we're going to have a look at bond energy calculations. For this task, I'm going to be referring to the bond energy calculations 2 worksheet that I have sent out to you. So we're going to start with question number 1, and I'm going to show you the technique of how to do this. So the first step would be to write out the question that we have been given. So the idea here is, if we relate this back to the bond energy profiles, we are trying to work out the amount of energy that is taken in and is required to break the bonds, and working out the amount of energy given out when we are making the bonds. So remember, the reactants have to have their bonds broken. So on this side, we are breaking the bonds, and then the products have to be made. So this time, on this side, we are making the bonds. The bond energy is the energy associated with a bond. That's either the energy that is required to be taken in to break that bond, or the energy that is given out when that bond is made. And you are given a table of these pieces of information. So if you have a look at the top of the worksheet, there's a table there. You are not required to learn these numbers off by heart. Any numbers like this that you need in an exam would be given to you. So the first step that we would want to do is we would want to divide our page in two, because we want the breaking and the making to be separate. And we need to look at the total amount of bonds that we have got on each side. Now, something that's important to take into account here is that this question has some 2's in there. So what that basically means is we have got 2 of this molecule here. So not only is it HH, if I get rid of that 2 there, we've actually got HH and an HH. And same as on the other side, that 2 there means we've actually got 2 of this particular molecule. So we can then lose that 2 here. I always find it useful to draw it out so that you don't forget that that number is there. The 2 that was over on this side here does not relate to this molecule here. It only relates to the molecule that it is next to each time. So we're going to count out the total amount of bonds that we have got on each side. So over on the left hand side, we have got 2 of these H to H bonds. What I do is when I've taken one of these bonds into account, I cross them off to make sure that I've accounted for all of the bonds. So if we look at the table of data, the HH bond is worth 436 kilojoules per mole. So it'll be 2 times 436. And then if we type that into a calculator, 2 times 436 gives us 872. Also on this side, we have got a O double bonded O, and there's just one of these. And if we look at the table of data, an O double bonded O has a value of 498. And then all we need to do is add those two values together to work out the total amount of energy that has been required to break bonds on this side. So adding those two numbers together, we get 1,370. Okay, now we're going to move to the other side and have a look at the energy that is being given out for making the bonds. So over here we have only got one type of bond, and this is an OH bond. You can see that bond here, and you can see that bond here. So it's not an OH and an HO, they're all the same thing, because it doesn't matter which way round you write it. You could write it either way round, they would both be the same thing. And because there's 2 of the molecule, in total we've got 1, 2, 3, 4 of these particular bonds. So we look for the OH bond on our table, and the OH bond has a value of 463. 463 times by 4 gives us 1,852 kilojoules per mole. And that's it for that side, that's all we need to do. So the final bit is to work out that overall energy change, because remember we're referring back to this energy profile diagram where you've got your progress of reaction at the bottom and energy at the side, and we're trying to work out whether more energy is given out overall or more energy is taken in. Well, simply looking at the numbers, you can tell already that more energy is being given out because this number here is bigger than this number here. So to work out the overall energy change, all we need to do is the left-hand side take away the right-hand side, like so. So 1370 minus 1852 gives us minus 482. And as you can tell from the table, the units for this are kilojoules per mole. The fact that this comes out as a minus number tells you that it is exothermic. It means that more energy was given out in the making of the bonds than what was taken in to break the bonds. If we relate it to this energy profile diagram, like we did in the last video, we can see that this amount of energy here that was put in to break the bonds was the 1370. This amount of energy here that was given out making the bonds was 1852. So overall that energy went down, hence why it's a minus number, and hence why it's exothermic overall.